Business? Yes.
Yep. Well, thank you all for it, all those who did attend the AGM, but now we have our monthly talk, and it's given by Jerry McCarthy, who's a volunteer at the TNMoC. He used to write software in areas such as retail systems, cryptography, and internationalization for a global computing company, but he now volunteers at TNMoC, talking to visitors about the witch. Come in, please. Which he's going to talk about this afternoon, EDSAC, the Argus 500, and the museum's slide rule collection. I've still got a slide rule. Don't use it very often, I have to say. Jerry takes an interest in other early computers and crypto systems, such as Enigma and Lorenz, and the breaking thereof. So he's going to talk to us about the witch simulator or emulator. We were having a discussion before as to what the difference is. Jerry, over to you.
We'll get a line.
Yeah.
That should work. I know.
Wouldn't work for you.
Let's see if that is working. Seems to give up this thing. I think probably best to use that
Okay, try it.
on there.
Didn't work.
No.
Oh, good. Okay.
I think there may be some people still sitting in the that don't realise that we're in here. So we literally just knocked on the door and we'd say, there was no indication. Yeah, well, this is the room, so. Well, there's several people in there actually, so it might be worth. Do you mind if I just pop in?
Yeah, go.
Volunteering, I think we're about.
So this is what the online people see, is it?
Yes.
Yes, good.
Yes.
Because I like to keep an eye on, as I change slides, that it changes there. Okay.
You may see that sitting somewhere else. You know, welcome. Sorry, it's is what anyone missing. Well done.
Well, good afternoon, everybody. I'm slightly nervous in the fact that the project lead for the witch is sitting right in front of me, but so I'm going to talk about this computer, the witch, and let's just see if I can get it to change slides by one means or another. Yes, so I'll be talking through three main topics, which is a brief history and why it has at least two names, a general overview of the hardware, and then writing programs for the witch, including an emulator. The original title of this talk was The Witch Emulator, but as far as I know, there's at least two others, and there may be more, so mine is merely one minor version. So, why has it got two names to start with? A bit of history. In 1949, design of the computer, the witch, or the Harwood-Decatron computer, began at the Atomic Energy Research Establishment at Harwell. I've stolen all this from the TNMoC website, by the way. Where there was a pressing need to automate the calculations then being performed on hand calculators by humans, computers, as they were then known. In 1952, the construction was completed and it was passed to the mathematicians to exploit its reliability. When required, it ran for more than 90 hours a week in its first year. I don't think we're managing that now. In 1957, the machine became obsolete and was offered in a competition to various educational establishments proposing its most appropriate use. And the competition was won by the Wolverhampton and Staffordshire College of Technology, who renamed the machine to the Wolverhampton Instrument for the Teaching of Computation from Harwell, hence the witch. And it's perhaps fitting that we have Halloween in only 2 weeks away as well. The machine was recognized by the Guinness Book of Records as the world's most durable computer, and it was then acquired by Birmingham City Council for display at their Museum of Science and Industry. In '97, the museum closed and the machine was put into storage. But following TNMoC's successful proposal to restore it to working order, a long-term loan was agreed, and it's still on loan to us. And in 2009, the machine was moved to TNMoC, which is an independent museum situated within the Bletchley Park Campus, I hasten to point out. 2012 restoration was completed. You should take a bow at this point. And it was again recognized by Guinness World Records, this time as the world's oldest original working digital computer. And today it is one of the museum's most popular exhibits. And our visitors really love to stand and stare at it while it clicks and ticks and flashes its lights and so on.
I'd make an argument that never known as the Harwell Decatron computer.
You may.
It was Harwell.
Sorry? Oh, what was it called?
Harwell.
It was just called the machine or something. Was it? The Harwell computer. Thank you.
They published. It's in Who Wrote Faster Than Thought? Vivian, no. Yeah. Faster Thought. I think it only acquired the name Harwell Decatron
Yes.
when it got to Birmingham.
Okay. Oh, thanks. Okay.
So I would be pedantic.
Well, that's fine.
Sorry?
They'd only got one, so they wouldn't.
Oh, that's right.
Decatron.
Yeah, it was only known as the Harwell computer,
Hmm.
and then by the time the Cadet came out of Harwell, they'd forgotten about any exit competition.
Hmm.
Sorry, I'm really pedantic.
And if you want to read more, www.tnmoc.org/which. A general overview of the hardware, and I'm happy if pedantic people want to drop in. Overall view of the machine. The most interesting part from a lot of people's point of view is the storage mechanism. You can see rows of decatrons, and each row of decatrons contains 8 decatrons, each of which holds a single decimal digit, and it's decimals, so the range 0 to 9. And the leftmost one is a sign, which is either 0 for positive or 9 for negative. Negative numbers are held in a complementary form, so that, for example, -1.70 is held as 9 for the minus sign, followed by 8 and 7 nines. And there's also a -0, which has interesting side effects, which I hadn't really comprehended the reason for, but I'll be getting onto that in a while. Those of you who saw my talk about the Kiev computer, which I gave about a year ago, I think it was, will remember that there is a -0 in that. And I've subsequently been told there are all sorts of machines that have -0s as well as +0s. And there's a fixed decimal point after the first decimal digit. So it's like, and you might be able to see in this picture that there's a little black dot on a piece of cardboard dangling down between 2 of the decatrons at the left-hand end.
If you'd like me to be pedantic, it's worth saying that's only convention. There's nothing special about the circuitry that enforces that. It's just convention that states that's how the numbers are treated.
And indeed, I violate that convention in most of the software I write.
So,
Yes. But it does affect multiplication, though, doesn't it? Because it determines where the value ends up in the accumulator.
Yeah.
Yes. Being pedantic. So the range is therefore plus or minus 8 zeros to plus or minus 8 nines. Now, how much of a memory does the machine have? Well, 8 nines fits into 27 bits, and with a sign bit that makes 28 bits, which when you round it up to a whole number of bytes is 4 bytes. And there's 90 rows of decatrons in the memory. So you end up with approximately 360 bytes. So you've got something that's like 8 feet tall and almost a yard wide. Just the core, the memory area, it's 360 bytes. But it's amazing what you can do with 360 bytes. The memory is numbered starting at locations 10 through 19 in the bottom right, and goes up 20, 30, 40 to the top, and then starts again at the bottom, 50, 60, 70, 80, and then the top left is 90 to 99. There's a slight quirk that the first 7 has the lowest numbered row at the bottom and the highest numbered row at the top, whereas for the memory boxes 80 and 90, it counts downwards. And if you look closely, you can see there's some difference in the design of the hardware. There's pairs of relays down the middle of the 80 box and the 90 box, and there's only a single row of or column of relays in the others. If you want to multiply 2 signed 8-bit numbers, you need a double length accumulator, which has sign plus 7 digits, and then a second row with 8 digits. So you have a total of a sign plus 15 digits. And the range of the accumulator is therefore plus or minus that many zeros, up to plus or minus that many 9s. Not only does the memory hold numbers, well, data, but it also holds instructions, or orders as they're commonly called in the documentation. And each instruction is held as a positive 5-digit number, of which in general, the first digit is the order in the range 0 through 7, followed by 2 2-digit pairs, each holding an address in the range 00 to 99. However, not all entries in the address 1 field are actually physical addresses, or even addresses at all. More details later. That's just a review of the memory, just so you can see it all in one box again. Addresses in the range 00 to 09 represent address mapped peripherals and other items, which I'm going to list off rapidly. And whether the address mapped peripheral address is being written to or read from is crucial, because it can be a different device if you're reading from some number than if you are writing to some number. If you read, for example, from address 00, you get randomly the value 0 or 1, which you can use for rounding values when you're doing when you're truncating the accumulator. And as far as I know, this doesn't work on the machine itself, although it does work in my emulator. On the other hand, if you're writing to address 00, that is just a null location of address, which can be used with certain instructions to clear a memory location without wasting a real address. The addresses 01 through 07 are 7 paper tape readers, of which there are 5 on 2 shelves at one end of the machine, 1 on a table at the other end of the machine, and 1 which I don't know where it is. And maybe it doesn't even exist.
Technically, the 2 paper tape readers that are next to the printers are part of what's called the editing table. They're not part of the addressable paper tape readers. As far as we know, maybe Kevin can correct, we've only ever seen 6 readers attached to the machine. So whether there was ever a 7th, we don't know, but the circuitry exists for it to drive it.
So
why do you need all these paper tape readers?
We don't have that. You don't have that much storage, so you're loading. You can run programs from paper tape, and you can have subroutines taped in a loop in the other paper tape readers, So that each time you call a subroutine, it will clunk its way around executing the subroutine. And then when it's done that, it'll be ready to execute the instruction again next time around. We don't tend to run it in that mode, to be honest, because the paper tape reader is fairly damaging to the paper tapes, in fact, and it makes a lot of noise. So we tend to load stuff into the memory and then execute it from the memory. So those are the 5 paper tape readers that we do know about. And we tend to load software into the top rightmost one of the 5. And we rarely use the other 4. I think there's a noughts and crosses program that does, isn't there? Mm-hmm.
Go backwards. Never been able to identify the manufacturer of those paper tape readers. Somewhere years ago, I read some notes with it which were in French. I can't help thinking, because those machines were in use at Harvard, they came from what's the big Canadian project? Half the Harvard people went up to Canada, nuclear reactor. So they came back from there. French Canadian. I can't track it down any further.
I believe they're made by ATE, but we don't know where they came from.
How are we using these? Because for which I didn't call it much, I hate them. For the hardware machine, they were using it connected to sort of Geiger counters and so on to record. So there are a lot of them about. I never managed to find them match. Sorry.
So the tape readers are mechanical. There's no optics involved. There's just 5 pins that poke up, and if they go through a hole, then that counts as a hole, and if they don't go through the hole, then it doesn't. And there's, of course, in those days, there were no particular standards for paper tape coding. So EDSAC is different. The which is different. ITA2 that Colossus and so on use is different. And in this case, for the Harwell computer, also known as the which, you have some single hole codes for plus sign, line feed, space, carriage return, and minus sign. And there's a note in the documentation that says that actually you don't use these on the tapes, line feed and carriage return. Because I guess there's no meaning to a line feed or carriage return on a tape, although there is a printer, which we'll get to, where they would be used. Then you have various codes for the digits in the range 0 to 9. Now, when you have a program, before the actual program that you want to load is punched, you have to punch a block marking character, which runs in the range B0 to B9, and they all use 3 holes in a special code. And that one I see, oh yes, a 5-hole one. Oh, sorry. And then we have asterisk, decimal point, again not used, figure shift, the letter N only. There's a mysterious one in the book that says letter question mark only, so I don't know what actually is missing from there. And then there's an erasure, so you can just stick a 5-hole character and it ignores the character. So I've covered the paper tape readers. You can write to 1 or 2 printers, which are write address 01 and 03. Note that these overlap 2 of the paper tape addresses. And you have 2 more punches on the table, which I now know aren't actually part of the which configuration. The printer is not in the best of shape because you might be able to see there are some odd spaces, and there's rather more in some of the rows. There are rather more letters, rather more digits than there should be. But it's close enough to work out what a program is doing. And then we have yes, 2 tape punches, which I don't think we have.
We have one.
Okay. And it's on the table, I guess. Yes. And then we have reading or writing to address 8, which is half of the computer, half of the accumulator, or to be more exact, 7 digits of the accumulator plus the sign. And you also have reading or writing to 09 to read or write the whole 15 digits of the accumulator. And you can't actually really read the 15 digits of the accumulator because you can't put it anywhere else, because there's only one 15-digit register. So that's just a summary of what I was talking about. There's a rather fine control panel. Some, quite often our visitors will say, well, where's the screen, or where's the keyboard, or things like that. And in fact, this is the best we have for a screen. And it's various lights telling you what the status of the machine is, various switches to, for example, reload the machine or do various diagnostics. And there is to the right a keyboard, which you can use for putting instructions into the machine and executing them. There's also a control switch. I don't know if you can see it very well on those of you at home, that's used to switch either the tape reader into circuit or the keyboard on the right into the circuit. So you can load software either through the tape reader or through the keyboard. Now let's talk about programming. And there's only, I'm going to go through all the instructions that it can execute, but don't worry, there aren't that many of them. So firstly, you remember I said there were 5 digits in the instruction, 1 for an instruction code, and 2 pairs of addresses. So for instruction 1, you just add a sending store, the store on the left, the store which is addressed in the leftmost pair of digits, into a second store. An important thing to realize is that the machine cannot cope with reading and writing to an address, to 2 addresses which are in the same box, because it's only got circuitry for accessing one of the rows of decatrons in each box. 2 is a slightly more complicated version, that it can add the sending store's contents to the receiving store's contents and clear the sending store. And this is something that you need to do because you cannot store a value. You can only add a value to the receiving store. So there's no way of clearing a store unless you use an instruction starting with 2 and then using the address of the store you wish to clear, and then finally the drain, the address 00. 3 and 4 are effectively the same, but for subtract. 5 is a multiplier, so it multiplies a multiplican by a multiplier, which are once again 2 separate addresses in 2 separate blocks, and it puts the result in the accumulator. And there's a division to do the converse, with a remainder in the accumulator. 7 says in the manual transfer positive modulus, but in fact by experiment I've determined that it actually adds the positive modulus to the receiving store rather than transferring the positive modulus. Just a simple example. If you have an instruction 11020, you are basically adding the contents of 10 to the contents of 20. So you, in this example, you're adding plus 1.5 to plus 7.5, and you get plus 9. If, on the other hand, you use function 2, which means the first digit is no longer a 1 but is now a 2, then not only do you get 9 in the 9.0 in the receiving store, but the sending store is cleared. That's just a repetition of what I just said. A and B must be in different locations, different boxes. I will gloss over the subtract because that's remarkably similar to multiplication, except when it isn't. What did I just skip? Multiplication. It multiplies on a contents of the first address by the contents of the second address, clears the contents of the second address and leaves the result in the accumulator. And then there's a division. That seems to be out of order, really, because that's subtract again. Sorry. Then we have a division, which divides the divisor into the accumulator. The quotient appears in the second address, and the remainder remains in the accumulator. Which is something I just said. The positive modulus is added to the receiving store rather than just literally transferred. Then we have a whole batch of instructions, all of which have as the first digit a 0, and as the first 2 digits are not in the main, if at all, addresses. Now, a conditional jump is actually 2 instructions, because you first of all have to set a flag depending on the store that you're testing to see if it's positive or negative, and then make a jump based on whether the test store is positive or negative. So that covers the first 4. When you want to load a tape, you need to use an instruction to find the beginning of or to find the block number which immediately precedes the program that you're loading. And that is also conditional based on whether or not a previous test store is positive or negative. Then there are 2 print instructions, which are not actually print instructions, they just prepare the system to print. The actual printing is just a matter of writing, or adding, I should say, the number you want to print to the printer. There's a shift instruction, which I'll go to in slightly more detail shortly. And then there are 2 halt instructions, 001, which stops the machine and lights a light that says finish, and 02, which stops the machine and lights a light marked signal. And then there's a null instruction, which is just all 5 zeros. In the documentation that I've been looking at, the word control is rather overused because it's used in one place to mean the results of a store test instruction. And in another place, it's used to mean an instruction to which a jump instruction goes. Just a simple example of a couple of tests and jumps. So if I've got 6.5 in location 30, and I do is it positive or is it negative, then I get results of the test as either yes or no. And if there's minus 6.5, then I get the converse. And then a jump instruction such as 02130, unconditional jump to location 30, or 2230, which is a conditional jump to location 30, depending on the previous sign. I've already mentioned the block markers, which is a conditional instruction dependent on a previous location test, which I guess could be used to decide whether or not you're going to execute a subroutine or some such. The machine comes with 2 initial orders, which are always executed when you do a certain keyboard manipulation. The first one searches for block 1 on the tape on tape reader 1. But the instruction, if you're using this instruction in your own software, then you can make it do searches for other block numbers on other tape readers. And then we have a 21 instruction, which is a jump instruction. So the two initial orders effectively rattle down the tape in tape reader 1 until it finds block number 1, and then it transfers control to the tape reader 1. So the tape reader 1 is in this configuration effectively being used as memory. The tape doesn't need to be read loaded into the reader at block number 1, because it will just skip blank tape until it finds the block number. Two instructions for printing. As I previously said, printing a number, you just add the number you want to print to the printer. There's a shift instruction, which is rather fun. By default, no instruction is shifted, but you can select to shift left by a factor of 1 or right by 7 different values when you're transferring a number to another location. So effectively, you can do multiplications or divisions by 10 by doing a shift. These are just 3 minor instructions: a null operation, which doesn't do anything, and then there's finish and signal. And the program can be made to continue after a finish instruction by operating a pass finish switch, except that doesn't seem to work on the machine, or that works on my emulator. And then there's a pass signal switch, which does work on my emulator and on the machine. So those two are the pass finish and pass signal switches. Now to an emulator, which I wrote. I started writing it during the pandemic, and so it's been visited and changed quite a lot over the past few years. I don't disregard the fact that the machine and the emulator don't quite agree with each other. For example, if you divide +4.0 by +1.0, I would have expected the result to be +4.0. But in fact, the quotient is +3.79 on the real machine. Although this, excuse me, although this behavior depends on the signs of the divisor and the dividend. And I seem to remember the book of how to program this machine indicates that it works better for negative numbers than positive numbers.
It's a side effect of the 9's complement.
I haven't implemented this in my emulator, although maybe I will one day. The distinction between the representations -0 and +0 hasn't been implemented either, because it's not easy to do that when you're writing in C on a PC architecture. But I might implement it in due course. So I'll just go through a few of the controls on the emulator, starting at number 1, wherever that is. Number 1, tape reader 1. So the first 4 tape readers I've implemented are blocks 1, 2, 3, and 4. And then 5 is effectively a tracing box. So there should be 5 readers. I've only done 4 to keep the space down a bit. 6 is the first memory box, 10 through 19, and then the other 8 are on top of that and to the left of that. 7 is a printer simulator. So as I print things, they appear in that print box. 8 is a buffer in which I create lines before I print them. And that's a feature that's not at all how the which works. Number 9 indicates 4 different buttons which load programs, run programs, single stepper program, and halt. So you can sort of do that through the keyboard on the machine. 10 is closing the program, closing the emulator. And also below it, you'll see a button marked VFD, which is vacuum fluorescent display. And that's because I do like to connect sometimes point of sale displays to my software so I can get a good view of what I'm doing. Now, where have we got to? 11, tracing box on the left. So tells me what's going on, tells me how it fails, and so on. 12, on the machine, you may have noticed that some of the decatrons are very bright and easy to see, and some of the decatrons are quite dim and not so easy to see. They're functionally equivalent, but when we write software, we try to put the numbers that our visitors might be interested in on the bright ones so they can just read what's going on more readily. So I have at the bottom 2 items in Mark 12, which are effectively the 2 rows of bright ones, copies of the signals in the values in the memory. 13, sound effects. The sound effects are nothing like the real thing, but it helps to slow the machine down if I'm trying to see something that's happening. 14 is the initial orders. The first 2 instructions that are always executed when you do a certain combination of key switches to start loading a program. 15 has 3 boxes marked test, which is the result of a test instruction. Then an overflow, sorry, a shift in alarm, a shift number, so that if I've done a shift instruction, I can see what the shift value is. Then there's an overflow flag, and finally there's a rounding flag. You may remember that I commented that you can either get 0 or 1 out of instruction 0, and that works on this. That I think is 16 print 16. The machine the emulator runs in 2 modes, either paper tape reader mode or Decatron mode, and it switches between the 2 so that I can just keep track of whether I'm executing a program from a simulated tape or from the simulated memory. You'll notice that the memory is full of X's, and that's because when you switch the machine on, the real machine, you have no idea what the contents of any of the memory locations are. And the same applies to the accumulator and the drain. And on the actual machine, we have to, if you're loading a program, the program you're loading must clear all the locations it's going to use before it tries to put instructions in the memory. Sorry, wrong way again. When you write a program for the which, you actually have to write 2 programs, because you have to write a program that you want to run, and you have to write a program that loads the program that you want to run. So here's a simple 1-line instruction, which is the 4th row in the text, which is just a halt. But if I want it to execute a halt in the memory, then first of all, I have to start with a block marker for the initial orders, B1. Then I have to clear some location. In this case, I'm clearing location 40. Then I have to add a number from the tape reader into location 40, where that number is the halt instruction. And then I have to jump to the place where I just wrote the halt instruction. So that's effectively 3 instructions to execute 1. And you can just see that I've loaded loaded the instructions into 40, which is the bottom of the box marked 40, and I've executed it, and it's come up with a finish, which is the value for 00100, excuse me. There's a lot of it around, isn't there? So a slightly more interesting program that I wrote recently for the visitors who like to see the machine running and who like to know what it's doing and understand how it's doing it. There is this rather fine online encyclopedia of integer sequences. And I decided to write a program to do the Fibonacci numbers starting at the beginning and going all the way up to 6324596. It's an old school machine, so I did an old school flow chart, which I won't go into too many details. And this is the first half of the program, which effectively clears most of the memory locations it's going to use. You'll see they're all twos, and then there are location addresses followed by 00. So they empty the addresses I'm going to be using. The exception is where I'm loading the value 1 into location 50. And then the rest of the program which actually does the work. And I'm not going to go into the full details of what exactly every instruction is doing, but I guess you all know that Fibonacci series is just a matter of starting with two very small numbers and adding them together and adding the number you just got to one of the previous numbers that you had, and then repeating this over and over and over again. Now I do have a demo, which maybe I'll save till the end because it's a bit fiddly changing this display over, isn't it? But the result is, as it runs the Fibonacci series, it produces a value in location 39, which is one of the bright ones that we always put our displayed numbers in. As I said later, my program simulates the printer and produces an output file, which is actually contents of the printer. And it goes up to 6324596. And even though I've put the decimal point in where it's generally held to be, I'm in fact treating all these numbers as integers rather than decimal, fixed point decimal. If I want to load programs, having written a program on my emulator and got it working, if I want to load it into the real witch, I can then write a program. I can then put the file I created into a program, which I've called a text-to-PTM, which is compatible with the paper tape punch that we keep in the workshop behind the witch. And here we have the Fibonacci numbers, which I managed to persuade the printer to print. And it's a bit untidy in places, like there's a plus sign where there shouldn't be a plus sign, and there's spaces where there shouldn't be spaces. But in general, the numbers match what they should be. Now we have some more discrepancies, which I only understood about 3 weeks ago when I was having a conversation with Delwyn. That subtraction is effected by adding the 9's complement of the number being subtracted. And I do admit this is just a reformatted copy of the mail that Delwyn sent me. Yes. And you get extra points for using the word affected as well. So if I add -1, which is 7 9s and an 8, to +2, which is 7 0s and a 2, you end up with +1, which is what you'd expect. +2 plus -1 is +1. Perfect. On the other hand, if I'm adding -1 to +1, then the result is actually -0. because the behavior that worked in the previous combination of numbers doesn't work here. So +1 plus -1 is -0. And I had this conversation with Delvin because I was using a counter which I was decrementing to calculate my Fibonacci numbers, and it was stopping in the wrong place. So brief email exchange, and now I understand. But unfortunately, it means actually that my emulator differs from the hardware at the moment. And the last discrepancy is, which I consider to be an improvement over the original machine. If I try and read a location that hasn't been cleared, that it gives me a warning box saying you are trying to read an uninitialized location. Because I have occasionally written software on my emulator and then tried to run them on the real machine and found it doesn't actually work because there's random numbers, not to mention random signs, in certain locations I was trying to read. That's a rather nice logo model that we, I think, was donated to us at one time. And although I'm saying thank you for your attention, I do plan to try and run the demo now. And I might need your assistance here on this strange laptop.
Me too. So should we close that presentation?
Yes, you can.
down?
Don't need it again.
Okay. So
You will need to go to this USB disk.
which is probably
Toshiba.
D,
Yep.
and then
And then
which talk? No.
yes. And then just one line up where it says JWitch 6.5.
Okay.
Just double click on it.
That.
Ah,
Okay.
good. And that's on the screen here.
That's not yet for people at home. We need to go back in there. A little bit delay. Got it. And then share.
Yes. Is that one?
That-
Yes.
Share. Okay. That's right.
Not from that black block over the top of it.
Still doing it. Darwin, can you
You not drag that to the top. It's disappeared by itself.
right. Okay,
Oh,
so
that's good.
do you need to run?
I do. But presumably it's now just runnable. Good. Okay. So first of all, I use the load button to bring up a list of programs that can be loaded. And you may be relieved to know I'm only going to run one of them. And now the program is loading. So I've just loaded the paper tape reader in effect, rather than loading the program itself. And as I said, when you're writing a program to run on the which, you have to write a program which incorporates that program and does the loading. So the run then starts. You can even see the mouse, can't you? Neat. And then strangely it stopped. Maybe I'll turn the sound off because maybe that's not liking that.
Who enjoys sound?
No, that's not right. Let's try that again. Oops.
Hear that.
Right.
Back into Zoom. I'll turn off the sound. Shares
Yes.
on here.
Yes, because I think that might have upset it.
Load.
Yep. Okay, let's see how it goes from there then.
Very quiet ticking.
Yes. I'm going to turn that if I can.
No, don't lose it.
Yes. It stopped again, isn't it? Well, I can just run it by hitting the so at the moment it's loading the program into various memory locations. Ah, all right. Yes. Now, you might have noticed that it was loading starting at 60 and up to 70, and then it jumps from 70, in fact, to location 40. And that's because when I tried running it on the real machine using block 70, there were a number of decatrons that were misbehaving. So I had to quickly fudge the program to transfer to a block that was misbehaving less. So I'm going to turn the sound off, and then you can see it running at a reasonable speed. You've got the Fibonacci numbers appearing bottom right, and the actual counter that I'm decrementing is bottom left. And there's a little box in the middle, which is telling me which instruction is being executed and what the instruction is. Then it's got to the bottom, and it's executed one of the halt instructions, namely the signal instruction, which I can then make it skip past by pressing pass signal. And now it just starts again. And we leave it running sometimes when we want to change from the standard programs, and if I'm in charge. And the values location 39 and location 38 are both in nice bright decatron rows so that the visitors can see what's going on. So that completes my talk. Let me just clear this off. I won't actually delete anything in case it loses your Zoom connection again.
That's okay, well,
Yeah, you can just,
yeah,
okay.
there we are. Okay.
And are there any questions? Sir,
Matter of interest, how long does that program take to run on a real machine?
about 20 minutes.
You hang on a minute while I get the,
Can you say a bit more about how you wrote it?
okay, I think if we need to get better now.
Okay. How I wrote it.
Language and
I wrote it in the language of the machine, which is just 5 decimal digits per instruction and
yeah,
8
but
decimal
the
digits.
underlying, is it in C? Is it in Visual Basic? You must
the
have
actual
written.
emulator.
Yeah.
Oh, sorry. Yes, the emulator is written in Microsoft Visual C 6.
Visual C.
Runs very nicely on my XP development machine.
XP.
Wow. How quaint.
With the Teletubby hills and things.
Yeah.
Yes, sir.
On the, on the real machine, why didn't they implement some software to, sorry, hardware to clear the entire machine on switching it on? Would that have been possible? Obviously, you have to zero eyes or clear all the decatrons before you use them. Why wasn't that done as an individual step or something like that?
I can take that. That would have added a great deal of complexity to what is already fairly simple hardware. Implementing a complete counter and what would be several line programs to run autonomously. Quite a lot of extra relays.
I guess you'd put it in the initial orders, wouldn't you? So the initial orders would go from 2 instructions to 92 odd.
In practice, how do you track the decimal point when you're doing, more complex calculations?
It's like a slide rule. You have to do it in your head.
Well, on the machine, if you want it print. Oh, I see. You mean you always.
If you want to do scaling, then
That's what I mean. Yeah, is there some technique that you use?
yes.
You've shown us that you multiply into the accumulator and you divide using the accumulator. Is there any way of getting the accumulator into the rest of the world?
Well, only in bits. There's
Can you move the accumulator to an addressed store location?
only half of it at a time.
Oh, but this is addressable. Okay. I didn't see anything in the instruction that said move accumulator.
Well, there isn't an instruction because the accumulator is just a memory location.
Oh,
But it does have 2 addresses, which is 09, which gives you the sign
that's what I was looking for. The 09 and whatever. Yeah.
08.
Thanks. The rest is familiar.
David Holsworth.
Hi there. I would be really interested to know to what extent this machine ever did any computation for which somebody really cared about the answer.
Yes.
Yes.
And please, do you have any examples of software that actually ran in its life at Harwell?
Yes. Yes. Oh, sorry. Can you hear David?
I can hear you.
Oh, good. Greetings. No, we have 2 examples, and one is something incredibly complicated for calculating the size of bubbles in heat exchangers. The closest we've got, the oldest we've got, is when Wolverhampton published a programming book which featured the machine. There are some examples at the back of there. But and the only other reference we've got of it used seriously that I've tracked down and is apparently believable, when they built Calder Hall, the metal frame grid that supported the core, they calculated how much it would deflect when they put all the it on, and that was the first use that's recorded of the machine from Harwell. And don't forget, it wasn't used as a sort of Harwell couldn't afford printed mathematical tables. Literally couldn't, and you couldn't get them as well. So more often than not, it was run just to produce tables. Oh, and the random thing is somebody at Cooker Arbor told me, somebody said they were quite interested in Monte Carlo analysis. But it would take about 20 years for that machine to run Monte Carlo, so hence the random.
Roger Norton, would you like to open your mic and ask your question?
I tell you, yes, I was, I guess as I went through, actually, I was quite interested. Firstly, I say I was rather shocked to realise I'd studied which at college in the 80s, because I'd still got some of the lecturers there that were aware of it, and it was an architecture I actually studied early on. So I was very shocked. Yeah, no, there's a few as I went along. I recognised a number of features. It takes the 5 holes. I recognise that very much because that's a good way of getting rid of any errors. So fixing the tape as you go with having the 5 holes are punched across. So that was a very familiar one with punch cards and everything else later on. So it's quite a good use of it. But my main query was, I bet you were saying it was 20 minutes to run the Fibonacci sequence. Would any plans to emulate that in your emulator so it acts at a real pace, and also versus the decatron versus the tape speed?
No, I don't make any attempts to make the speed match the real machine. It just runs at whatever speed the computer I'm running it on runs at.
Do you think it would make a difference, or would it? Have you seen any results differently occur on the real machine versus your emulator in that regard?
The results are mathematical results are all the same, except in the case of my little problem with the -0.
Yes.
But
okay.
The fact that it's running at 10 times the speed of the real machine doesn't affect the mathematics of the results of the mathematics.
Okay.
Okay, there's a question. Is the emulator available? If so, where from, please?
Not really, no. It means I'd have to write manuals and provide support and so on.
Christine Arrowsmith, would you like to ask a question?
Yeah, well, I can see the question.
Okay, far away.
The microphone's up. Oh, yeah. I don't know where the other 2 emulators are these days. I know we used to have some communications with some people who wrote a couple.
Yeah, several people have written emulators, but as far as I know, none of them have actually chosen to publish them in a way that other people can use them, which is unfortunate. But
yes,
obviously, it's I understand the support implication. Extension if you did publicize it.
There was a very nice one that actually emulated the decatron, the orange light going around in circles and things, but that seems to have gone offline now.
Oh, Bob, the key Bob did that.
Jerry, you showed memory locations 80 to 89 and 90 to 99. I recollect, I can't remember whether Kevin or possibly Delwyn told me that those were added later. Wasn't the memory increased at some stage?
Yes,
The originals.
hence the rather clumsy add-on at the end.
Yes.
Yeah, there's 2 separate things there. So the 2 that are different are actually the first 2 stores that were built. And we have a photograph, the first published photograph, I think, of the machine before it was handed over. I think it's from 1951.
Well, that's the picture that's in Faster Than Thought.
Yes. So, and in that picture, there's only 2 stores on the machine, and they're in position of 20 and 30.
Right.
And it's those 2 store units. And what we think, because they used more relays in those stores, diodes were just becoming more affordable. I think what they did when they built the rest of the stores, they designed out the set of relays and replaced them with diodes instead, which is why you have, if you look at them, you can see there's only one set of relays in the down the center. They obviously had them all built by somebody because they're all very nicely wire wrapped and used. And for some reason, I don't know whether it was by design or by accident, but they got the addressing the other way up. So it's 7 of them are addressed from the bottom to the top. The first 2 are addressed from the top to the bottom.
Okay, thank you.
Gentleman in the orange and blue plaid shirt.
Just get a better feel of how fast this thing is. How long does the multiplication take?
It's 5 or 6 seconds, isn't it?
I presume that there's a big chunk of kit somewhere that actually does the multiplication.
It does multiplication by shifting and adding, just like on a manual calculator.
Oh, I see. So it's just so it's sort of a sequence of additions and shifts.
Yeah.
Ah.
Because an addition takes a couple of seconds and multiplication takes 5 or 6 or 7. Depends what the digits are that are being multiplied by what.
Presumably, division is by repeated subtraction.
Say that again?
Division is by repeated.
Presumably, division is by repeated subtraction.
Done by repeated addition of the complement.
Yes.
Okay.
With the fudge factor as well. All the fudge factor.
I think there's a video, isn't there, of the witch with somebody sitting there with a Bundesliga, and they're trying to keep up with the machine.
Yes.
So for, I don't know, a minute or so, I've seen this sequence.
Yes, I think we did a race, didn't we? Yes, with one of our volunteers on a calculator and another.
Well,
The speed of the machine, at least.
let's get it right.
But how much of the original machine is still there? I mean, are there any original decatrons from? Also, has everything been replaced? And
They're all original decatrons. They haven't made decatrons of that type since the 1950s, I think, or possibly early 60s.
all original.
Yeah, particularly the ones that you see that are faint. They only made those are called GC10As. They were only manufactured for a very short period before they were replaced by the GC10B, which is the brighter type. They're actually also faster, those, but not that the which requires the speed. So we know for a fact that all of those are from 1950-51 timeframe.
So much for the life of vowels.
Are any of like devices nowadays or like a bit like before using like the hardware or the design that the witch used?
Well, not really, because it was kind of a dead end for its design. It's a completely decimal machine for a start, and almost everything's binary these days. We don't use paper tape readers or paper tape punches very much.
The subroutines.
Subroutines still exist, yes.
Certainly the general principles are the same, and that's why it's so effective as a machine at teaching computing, because the basic principle of having input units, an arithmetic unit, a control unit, and output units, and memory, those concepts are obviously still valid.
Or Neumann architecture.
Yeah.
It did almost have a future. Plessy spent a long time trying to bring it to market. It was going to be called the Rascal. But I think by the time they'd actually done all the work to bring it to market, it was too bloody late, basically.
The time.
Can I just answer the question that we were discussing before your talk? Which is, what's the difference between an emulator and a simulator? The answer, according to our authority called Google, is that the emulator replicates the hardware and software. The simulator is what you do, which is just replicate the software.
So I'll have to rename all my emulators to simulators in due course.
Something. I have a quick question for you. Why was it called a decatron?
Because it's got 10 effectively it's got 10 neons. Actually it has 30, but you can it stops at one of 10 positions.
It's a Greek deca.
Yes, Greek deca. I think there are other trons of other numbers.
Trons, yes.
Yes. Isn't there a duodecatron, which is a 12 or something?
Okay. Oh my God. Jerry, thank you very much. You're welcome.
Yes.
Well, the number of questions demonstrates a level of interest. It was fascinating. Thank you, Jerry. I enjoyed it, learned a lot. And I can see where that's come from. Kinda. So that's been, can I announce that the next meeting on November the 20th, Thursday, November, Barry Landy will be talking about the Cambridge multi-access system. On December the 11th, Dan will be hosting his usual film show.
I better go on with that then.
The other thing Dan is exploring, I don't know if it's going to go anywhere, is a possible visit next year to Madrid, where they have what sounds like a really interesting museum. So still working on dates for that. Hopefully that will eventuate. So with that, thank you all very much for attending. It's been a splendid afternoon. Look forward to seeing you next month.
Thank you.
Thank you.
As a kid, I made other